Welcome to another video in our Amazon Cloud series. In previous videos, we've covered how to manually deploy a monolithic application to a single EC2 instance in Amazon AWS. And then we upgraded our capability by improving our DevOps positioning, where we created infrastructure as code and we developed a CI/CD pipeline so we can automatically deploy. And then we talked about how we can start scaling the different services of our application. And that mostly involved carving off each service and putting in its own tiers. Now we have a multi-tier application. So in this video, we're going to start our discussion about scaling our web application. So the first thing we're going to consider is, we have a single server. It has a certain amount of RAM and it has a certain number of CPU cores. How can we optimize our environment, our Nginx configuration or our PHP-FPM configuration or Laravel to optimize server performance? And that's what we're going to get to today. And then in upcoming videos, we're going to talk about scaling both vertically and horizontally. So if you like content like this, hit that like button and subscribe. Before we dive into the details of performance tuning, it's kind of important that we kind of revisit where we've been so you know what's already been done. So in the past, there's 8 videos on the monolithic deployment where we did it manually. Then we talked about doing some DevOps improvements and upgrading our capability, where we created some infrastructure as code and we created a CI/CD's pipeline. And then we started to talk about scaling individual services like database and the cache and the workers. Now we're down here on the web scaling. So that's where we're at. We've come a long way. There's a lot of videos out there. So if you're uncertain about any of the other aspects that we've already covered, go back and revisit some of those videos. As our example, we've been deploying a Laravel application, but this could be whatever kind of application that you want. This video, we're going to talk about performance optimization of some PHP-FPM processes. That's kind of PHP specific. Maybe it's a WordPress site, or maybe it's one of the other popular PHP frameworks. For our Laravel application, this is what the services look like. We have a web service, we have a database service, we have these workers that are kind of processing jobs from a queue. We have a scheduler that's putting jobs on the queue. And this is some of our underlying infrastructure on the right-hand side. We're not going to talk about the details of that, but we did initially do a monolithic deployment where all those services, we stuck them all in one EC2 instance. And that's great for environments like development or something where you just don't need to scale and you just want something nice and convenient. But when we really started talking about scaling the individual services, we ended up with a multi-tiered application. We carved off our database into a tier of its own. We're using Amazon RDS for that. We carved off Redis cache. We put it into an AWS Elasticache. In the last video, we carved off our workers and our scheduler, and we put that in a worker tier. So now we're just going to focus in on this web tier for the next couple of videos and just see what we can do to squeeze the best performance out of that web tier. All right, so what we're going to do is we're going to take a look at 5 kind of dimensions here on kind of improving our performance for our server. First thing we're going to do is we're going to take a look at each one of these kind of at a theoretical level. Then we're going to take a session where we log into the server and take a look at each one and how it's all configured. So first of all, latest versions. Installing the latest versions can have serious performance impact. As an example, if we look at this website where they're doing PHP benchmarks, we can see some of the benchmark testing that this website did for 8.1, 8.2, and 8.3. If you're running an older version of PHP, that performance is even going to be worse. But if you look down and we just scroll down to the benchmarks, they ran WordPress for a certain version of WordPress. The newer versions of PHP perform better. So they had more requests per second. And so that's what these little dials indicate. And generally that's true of any language. Usually language developers try to make it more performant. Same thing with frameworks. A newer version of the framework is usually faster than the older version. One of the caveats to that is sometimes there can be breaking changes for example, in the PHP code when you go from an older version to a new version. So you have to be kind of aware of what those breaking changes are and kind of refactor your code. The same logic is true for application versions. So for example, the current version of Nginx versus the version of Nginx that's 5 years old. My bet's on that the latest version is probably a little faster. So it's definitely an important thing to be running kind of the latest versions. Swap space. We talked about swap space back when we were provisioning our initial Ubuntu instance. We provisioned a T2 micro instance. It only has 1 gig of RAM. I had performance issues right away with that 1 gig of RAM. And so introducing a swap space was important. If you don't know what swap space is, it's kind of space on your hard disk that your computer can use as virtual RAM. Now, the biggest thing here is that this swap space is a lot slower than actual physical RAM. So you want to try to configure your application so that you're not hitting that swap space, but it's more kind of a contingency in case you over allocate RAM and your applications just don't crash. As a general rule of thumb, if you have less than 1 gig, you want to try to provision 1 to 2 times the amount of RAM. So we had 1 gig on our T2 Micro, and so we actually provisioned 1 gig of swap space. Now, if you have larger amount of RAM, so if you're bigger than 1 gig, then I found this formula. And these two formulas I found here on itsfoss.com, so you can go to that website to look for more information. Another aspect or another dimension here of making our application run the best it can run is application caching. So caching takes advantage of the fact that not all memory is kind of the same. If I read something from disk, or I have to query a database for some data, or I have to kind of compile a blade template to create some memory, that's not as fast as if I had that memory blob kind of in like a Redis cache, and I could just go and access that using kind of a key value pair, and I just want to grab that value for the key. Since we're talking about a Laravel specific example, let's go ahead and take a look at some specific examples from Laravel. First of all, for Laravel itself, under the documentation for Laravel, optimization down here on the deployment guideline, you're going to see a command called PHP-Artisan Optimize. That does a lot of the legwork for you for optimizing your PHP or Laravel installation. Just as a concrete example, let's consider one aspect of this. When you run PHP-Artisan Optimize, one of the things it does is it optimizes the config data. So config data in Laravel is stored in a bunch of configuration files, which are just PHP files. And so what this optimization does is takes those configuration files and it combines them all into a piece of memory and then stores that into kind of your Redis cache. Another area where things are cached are routes. Imagine every single endpoint that your website has to serve up has to go and figure out, given a route, what's the controller? Where am I going to send that route to? And so that lookup table or that information, that's important that we cache that. Again, running PHP-Artisan Optimize is one way to make sure that our routes get cached. And then let's talk about a specific example of where you might use caching inside your Laravel application. A common place where I find myself caching is anytime I'm going to use an API call. So for example, I have two kind of helper methods here. One is an LLM helper that I'm using under the hood, OpenAI's API, and then the other is like a geolocation helper that I'm using kind of Google Maps API. And if we take a look, they both kind of have the same pattern. When I construct this helper, I grab the API key from the environment variable, and then there's one public method here that takes a prompt builder. And so you imagine what we're doing here is OpenAI's API takes a prompt, like a chat that's been going on, and then it's going to generate a new response. The first thing I do is, given a prompt, I try to get that response from the cache. The assumption I'm making here is that if the prompt hasn't changed, then I'm okay if I use the old response that was already generated. I don't really care if, because there's some temperature setting that's for the OpenAI API, it might generate a different response for every time I give it the same prompt. I don't really care about that in this example. What I want is a single response. I'm assuming that the response is going to be okay to use, and then I go ahead and I cache it. So if you look at the caching mechanism here, so if we look at the caching mechanism for this git cache, I generate a key based upon the prompt, and I'm just going to get all the messages in a big array, and then I serialize that to a string, and then I MD5 that string. So that's my key. And then I go into my cache and I look for that key. If it's there, I return that value. Otherwise, I return null. If I get null, then I'm going to use the OpenAI API, and I'm going to go and create a new chat instance, and I'm going to get that response. And then at the very end, I'm going to add that response to the cache, which is kind of doing the opposite thing. I grab that same key from the prompt, and then I put that response that I just got from the API, and I put that in the cache. Then the next time I use this helper with the same prompt, I'm going to get a cache hit here, and I'm going to grab that response, and I'm going to return that response without hitting the API. One of the subtleties that you have to decide as a developer is how long that you're going to cache this data for. I've decided that for this particular instance, I'm going to cache this for about an hour. And after that, it'll leave the cache, and if you hit this again with that same prompt, you'll have to regenerate it. But 1 hour is kind of a good balance between having that cache not getting kind of broken or busted right away, and I have to kind of regenerate that response call on the API, versus having stale data in my cache. So that's a good trade-off for me on this one. And the only thing I see as I code review my own code here, I probably would take this, factor that key generation into kind of its own little private helper. That way, if I ever want to change how I'm generating the key, it's just in one spot. And I do a very similar thing over here in this geolocation helper. This time I'm using kind of Google Maps API, and you can see there's 3 kind of public endpoints. There's get address, so given a lat long, what's the address? Street, city, state. Or given an address, what's the lat long? And then I also have one other kind of public endpoint where I'm given 2 addresses, a from address and a to address, and I'm using the API to get directions. And all 3 of these will follow the same pattern. But if I look at this first one, let's just look at this one, get address. Given a lat long, what's the address? The first thing I do is I generate a key. And usually my key names, because the cache is kind of Redis cache, it has to be kind of globally unique within, my application. So I usually kind of use something like this to kind of generate this key. Is I put the function name, I prefix it to my key, and then I put in what makes it unique, the lat long in this case. That's what makes it unique. So that way, this function has its kind of own like namespace in the cache, and I'm looking for data in that namespace. So once I get the key generated, if I find that the cache has that key, then I'm going to skip all of this, and I'm going to grab the response from the cache, and I do the processing below. If I didn't get a cache hit, then I'm going to use the API, the Google API here, and I'm going to go get a response from their endpoint. Once I have that response, the first thing I do is I put it on the cache. And again, I have to set the cache time. And again, I've kind of struck a balance between having a stale cache and hitting that API all the time. I set the expiration for the values at about an hour there. All right, so now that we've covered kind of the application level caching, we talked about some specific examples of using data. You can also use page level caching. You can also have page level caching. Where this is kind of particularly useful is if you have a dashboard, like an executive dashboard that every day they want kind of a single report. What you can do is you can generate that page, and then you can just cache the whole page. So every single time the executive hits that, or any executive hits that page during that day, everybody gets the same answers. Otherwise, what could happen is, especially if you have kind of a database where it's just being updated continuously all day long, if you have queries on that database, the numbers slightly change. And by using page level caching, you can kind of circumvent all of those issues and get your performance gain all at the same time. PHP-FPM configuration, there's a lot of information here. I tried to include it all. So if you have to, go ahead and pause the video and kind of read through this. When we do our live demo, we're actually going to log in here in a bit, and we're going to cover all this kind of using the actual comp file itself. But I just tried to put all the information you would need in one spot here. So some of the information you need to be able to configure this comp file for PHP-FPM is you need to know the total amount of RAM you have in your system. Now, for the T2 micro, I know from the spec sheet, you have about 1,000 megabytes, let's say, of RAM. The other thing you have to be able to compute is the total amount of used RAM. So, in this case, we're going to try to allocate some RAM to PHP-FPM. We want to know how much of the total RAM is being used by other system services. For example, Ubuntu itself will take up some system RAM. And then we have NGINX run on the server. That will take up some system RAM. If you have other services like MySQL or anything else that might be running on that same instance, it's going to take up some RAM. And that's not going to be available to your PHP-FPM process. So you want to be able to compute this. Usually what I do is I shut down PHP-FPM. So you can use kind of the sudo service PHP-FPM stop. And then I can use free-h and take a look at both my total and the allocated RAM. And in my case, for that T2 micro, again, it's about 1,000 megabytes of total RAM, and about 200 megabytes of that was being used by other applications. So that means my available RAM, which is the difference between these two, is I got about 800 megabytes. Then I need to be able to compute this RAM per worker. And there's a lot of estimates out there, ranging from I mean, I saw things as low as like 40 megabytes to 150 megabytes per worker. I did find a script, and here's the link to this script. If you download this ps_mem.py and you run this script, then when I ran this on my server, I ended up with around 60 megabytes per worker. So that's the one I'm going to use for my case. And then my T2 Micro has 1 CPU. So that's kind of all kind of background information. Now we can get to kind of the comp file itself. So inside the pool.d directory, there's a comp file for every pool that we're running. I have one that's called demo_1.conf, and we're going to take a look at that in a moment. And then in there, there's these directives that you can configure. There's a listen directive that you can configure either for listening on a Unix socket, or you can configure it to listen to a TCP socket. The Unix socket has less overhead, so it makes it a little bit faster. And unless there's a reason why you need to use TCP, I would just recommend that you use the Unix socket. One of the reasons why you might want to use the TCP is if you have NGINX deployed on an Ubuntu instance, and then you have a number of other Ubuntu instances that are running PHP-FPM services, and you want to kind of use one NGINX instance as a load balancer in front of all those PHP-FPM instances, then you can use TCP sockets, and then the main NGINX will kind of load balance requests to each of those servers. So that's a case where you might want to use TCP sockets. Otherwise, I would just use the Unix socket itself. Then you have to decide what kind of process manager you're going to run. The three options are static, dynamic, and on demand. So static is you're always going to spin up a fixed number of child processes. This is generally the fastest of all of the PHP-FPM modalities here, because there's no wait time. These processes are just already spun up, they're already waiting, and as soon as a request comes in, that there's a child process that is able to handle that request. So it's definitely the fastest. And then in general, here's the formula for max number of children. So that's the total number of processes that are going to get spun up here in this case, and it's equal to kind of the available RAM divided by the RAM per worker. So in our case, available RAM was 800, RAM per worker was 60. 800 divided by 60 is about 13 processes, or 13 max children. Another modality here is dynamic. And in this case, what PHP-FPM is going to do is try to have always one child process kind of waiting, and it's kind of a hot standby. It's waiting for a request. And if a lot more requests come in and that one child process can't handle it, then it'll spawn up new processes up to kind of the max number of children here. And so you still set the max number of children the same as we did before, but you're also going to set the number of start servers, and that's going to be set to kind of your number of CPUs times 4. In our case, that's just going to be 4. And then you can configure kind of this min number of spare servers and the max number of spare servers. These are the number of idle kind of child processes that are hanging around, and then there's some recommended configurations for those too. And the third modality is on demand. So this is definitely the slowest of them all, but it uses the least number of resources, because there's nothing ever really running until you have a request. Then it spawns up a child process to handle that request. At some point, that child process is killed off. And then the final setting that we're going to take a look at when we configure the PHP-FPM process is something called max requests. This is important if you're in PHP and you have some, maybe a plugin or your code that has any kind of memory leak. And so what this does is, after a child process handles this number of requests, so you set this to say 1,000. After it handles 1,000 requests, then that child process is killed by kind of the overwatcher, and a new process is spun up in its place. So this is important if you have any kind of memory leak or anything like that going on. You want to have kind of this maximum number of requests set. And then the final configuration that we'll take a look at is the Nginx configuration. Now, we saw when we did the initial profiling of our application that PHP-FPM is really the thing that's consuming most of the CPU and most of the RAM. Nginx really wasn't the bottleneck for anything that we'd seen so far. But let's go ahead and cover, what are the configuration options that we have available to us for Nginx. So in the Nginx conf, there's really two things that you can set here. You can set the worker processes. That's the number of processes that are running. These are child processes, and generally this is set to either the value of auto, and it tries to auto compute the number of CPUs, or you set it to the number of CPU cores. In our case, the T2 micro has 1, so we'd set it to 1, or we could set it to auto. There's also a value called the worker underscore connections. And this is the number of connections that each one of these worker processes can handle. And so if you set this thing to like 1024, which is the max value, and what I saw, the recommended value in most of the cases, then every process that you have running can handle 1024 kind of connections or requests. Some of the other options that we want to look at when we look at Nginx Conf for compression, we want to make sure all our data is kind of compressed. So if I'm sending a payload over the network, I want to minimize that payload size. We could do that by compressing it on the server by gzip, and then the client or the browser will unzip it when it receives it. We want gzip on. Here's some other values for gzip that we'll take a look at. The other thing that we can do for our Nginx Conf is we can cache all our static assets. So static files like images or icons, CSS, JavaScript, we can add an expiration date and we can cache that. That can be a bit painful on machines you're going to use for development, especially if you're going to be pushing up new JavaScript files and you don't have a mechanism to bust that cache. You could quickly find yourself in a situation where you've changed the JavaScript, it's not functioning like you think it is because it's running the old version that's cached in the browser. So for any machine that you're using in development, I would recommend that you keep that off. But for production, as long as you have a mechanism to kind of break that cache when you do updates, then go ahead and set that out to a year if you want. Finally, we take a look at logging. And really, there's kind of two types of logs in Nginx. There's access logs and error logs. Access logs, every single resource you hit or you ask it for, whether it's a main page, a JavaScript file, an image, an access log entry is created by Nginx. You may want to or you may not want to have that access log kind of running. And that's kind of up to you. But one of the things you can do if you're going to keep it running is you can buffer the log. So instead of writing to disk after every request, there's a bit of a buffer in memory that it's trying to fill before it writes it all to disk. This can be a little bit quicker. Otherwise, you can turn the access log all the way off. What we're going to do now is we're going to log into our server and just really kind of dive into these last two one more time. Okay, so what I have here is a terminal window. And right now I'm sitting in a directory on my desktop called Laravel_demo. We're going to SSH in using a key file that I have in that directory. And we're going to log into our server. I'm just going to copy the IP address and paste it in there. And I'm going to go ahead and connect to that server. All right, the first thing we're going to do is we're going to take a look at our PHP-FPM conf file. And what we're going to do is change into the directory where PHP is installed. Just to orient everybody, it's installed in etc PHP. In there, there's only one version right now. I have 8.3. And then once you get to the 8.3 folder, you're going to see a couple of other directories. One is the FPM directory, which is what we're interested in right now. So we're going to switch to the FPM directory. And then if I look and see what's in that directory, I can see the pool. And then we were in here before where we created a bunch of pools. And so if I look at what's in the pool directory, you can see my comp file. There's really two comp files in there right now. One is the demo_1 comp. And then there's this comp file, which is the default one that is deployed when Nginx is actually installed. We're going to take a look at the demo_1 comp file now, though. In this comp file, you can see that there's a pool name. Demo_1 is the pool name. And as we scroll down a little bit further, so the first thing that we're going to notice is we can see this listening directive. And we're listening on a Unix socket at this point. This is a lot faster than the TCP sockets. I don't really need, in this case, the ability for a TCP connection to some other IP address. This Unix socket is faster and it serves my purposes. And this socket name was created from our deployment script that we talked about earlier in previous videos. And so there's a demo_1 kind of variable stuck in this socket name. As we scroll down a little more, we're going to skip the security. We covered this in the past about, the owner and the user groups and all of that stuff. But I want to get down to this possibility. So now we're starting to get into the area of static, dynamic, or on demand. What is the PM value? So what is the value for kind of what they call this process manager? What's the modality here for this? Is it static, dynamic, or on demand? Right now, we are set up for kind of this dynamic case. And then remember, in our slide deck, we talked about how probably static is the fastest one. So if you have a dedicated instance and it's just for one application, I would recommend that you go with that static modality. I'm going to keep it dynamic, and the reason I'm going to keep it dynamic here is we have that deployment script where I can easily spin up, instead of a demo_1 application, I can spin up a demo_2 or a 3. And each one of those will have its own pool. And I don't want to have these statically configured where each one's going to grab 50 workers. In that particular case, it can quickly kind of consume all the CPU and all the RAM. I'm going to leave it in this dynamic mode so it can start off with a minimum number of workers and then it can scale it up to kind of the maximum. So that's where I'm going to stick with this. All right, so now if we take a look at some of the numbers here, we talked about these numbers in the slide deck, but the total amount of RAM that I have is about 1,000 megabytes. The total RAM that's used by other applications on this particular instance is about 200 megabytes. That leaves about 800 megabytes for me to carve up and use for PHP-FPM. I also computed using a script, and we'll look at that script in a little bit, that each child process is going to use about 60 megabytes. And so if you take 800 divided by 60, you can end up with about 13. And so what I've set my max children to is something a little more conservative, but we're going to say around 10. And again, I'm being conservative here because I know that I might have demo_1 and demo_2 kind of run at the same time. And so I'm just kind of leaving a little bit of headroom for, when that scenario might happen. Based upon the information we saw on the slide deck, so I want to set this to the number of CPU instances times 4, which is going to be, I have 1 times 4. And we'll just make a little note here. So this is num CPUs times 4. That's the recommendation, so that's what we put it. Here for the number of spare servers, the recommendation is num CPUs times 2. So we'll put that as 2. And then for the max spare servers, this is num CPUs times 4. So we'll set that to 4 also. And then for these other things, this default value of 32 I'm going to leave. This default value of 10 I'm going to leave that also. Max number of requests before you respawn it, I'm going to set that just in case we have any memory leaks. I'm not anticipating it, but it's good practice to go ahead and set that to something that's kind of relatively high. I don't want to respawn every time, but maybe after 1,000 requests, it's okay to go ahead and do the respawn. And so that's how we're going to configure PHP-FPM in this case. So we're going to go ahead and exit out of here. Anytime I change a PHP-FPM conf, I need to kind of recycle the service. So I'm going to go ahead and do that. And so now our changes to that configuration file are in place. Next thing is, let's go ahead and get over to the Nginx area. So the Nginx is etc Nginx. If I look inside there, there's a conf nginx.conf file. So we're going to edit that. So we're not going to change a lot in here. Again, Nginx was not my bottleneck, but I just kind of want to go through, I want to look at what's set and show you where kind of those handles exist. So the first one is, obviously this first one is the user. It's setting kind of what user Nginx run under. We're not going to change that. That's the default user. But the worker processes. So right now, the recommendation is you set this to auto or you set this to the number of CPUs. And so I'm just going to go ahead, we'll hard code this to 1. We have 1 CPU, so we'll set it to 1. Inside the worker connections, this is where we're going to max this out at our 1024 value. All right, so then when we start to scroll down, the next thing that we're going to see here are the logging settings. Here's the access log, here's the error log. They're both kind of on. I'm going to leave them on. I'm not going to set a buffer for them. I'm just going to leave it the way it was. And my reasoning on this is right now, Nginx is just not my bottleneck. And I'm going to leave this until I find out that Nginx is my bottleneck, and then I'll come back, and if I have to do some performance tuning, we can take a look at that later on. The only setting I do want to make sure is gzip is on. And then there's some other values for gzip that are kind of commented out right now. I'm going to leave those commented out by default. And then the last thing that we talked about in the slide deck was caching kind of static assets. Because this is a development server, I know that I'm going to be changing CSS, I'm going to be changing JavaScript. I don't want those things cached at this point. So I'm going to not turn that on. So I'm going to exit out of here. I'm going to save this. And again, same thing. We're going to restart Nginx just to make sure that comp file takes effect. Before we move on, I want to just show you how I computed some of the free memory and total memory. And what I did is I shut down all of my PHP-FPM. And so I stopped that service altogether. Once I had that service stopped, then I used free-h to tell me the total number of kind of RAM that was available. It's about a gigabyte, 1,000 megabytes, and the total amount that's used. So this is about 290 megabytes. Last time, I think I was closer to 200, so maybe I should readjust my calculation and make it 290, but that's how I computed the amount of total RAM and then also the amount of kind of used RAM by other system resources. So I'll restart my PHP-FPM process again. And the last thing I'll just show is there's this ps_mem.py. And I left the link for that Python script previously in the slide deck. But we can run what we can do is we can run this command and that script, and it's going to give us an output that looks like this. So this is the total amount of memory that's used per process. And in this case, this is 30 megabits, if you want to call them. And I put 60 because when I ran this previously, I got a number around 60. This does use kind of some average amount, and depending upon how much you've been using your server, this may be higher or lower. So I'd be using it for a little bit and get a good average here. But I use 60, and that's how I got my number, was 60. So now we've kind of fine-tuned our Nginx and our PHP-FPM. Performance testing. Last time we used kind of a website called loader.io for performance testing. Perfectly fine site. It was created by, I think, SendGrid Labs, and certainly something to take a look at. I just want to look at different tools as we move along. We're going to run glances again here on our server so we can kind of get a look at the CPU usage and the RAM usage and everything. So right now, steady state, nothing really hitting this server. About 2.9% of the CPU is being used. 47% of the RAM is being used. And again, over here on the right-hand side, you can see kind of these processes. I have the PHP-FPM pool. Here's my demo_1. There's 1, 2, 3, 4 worker processes that are just kind of in this kind of standby mode. They're sitting there, they're waiting, they're ready for requests to come in. Okay, so that's kind of where we're configured at right now. What I'm going to do is I'm going to open up another tab. I know this gets confusing times. I wish I could kind of change the label here so you can see what this is, but this is on my MacBook Pro here. And there's something called AB, which is Apache Benchmark. And if I just hit AB by itself, you're going to get a bunch of these kind of options. And what we're going to do first of all is we're going to just hit it. We're going to use the -n option to set the number of requests. And so, for example, I can say AB-N, and we'll set the number of requests to, let's do 1,000. And then I can put in the URL. And assuming that I type that URL correctly, when I hit this, it's going to send 1,000 requests, not all at once, not concurrently, but kind of in a row to our application endpoint. And so if I just hit this, it's benchmarking, and then I'm going to watch over in glances, and you can see that my I'm at 54% CPU. Before I was idling around 3%. Haven't really used all the RAM yet, so I'm not really constrained on RAM. I'm not constrained on CPU usage at this point. This server, if this is the total number of requests that are going to come in, this server can handle that number of requests. And you can see here that it's already kind of created 100 requests. I'm going to jump out of this early because I don't think this is that interesting. So I'm going to hit Control C, and then you can see some data on the requests that it has entered so far. So far, based upon 1,000 requests, it's actually created 183 of those. Now it said 179 have failed, and I looked into this a little bit. There's a content length here of 179. These have failed because they're different content length. And I think that Apache Benchmark is looking for kind of the same content every time. So when you do the request the first time, you got 5,000 bytes, and then you do it a second time, you get 5,000 bytes, and you do it the third time, and then it would say that all those are the same and they're all good. This is a dynamic website, so every time I hit this front end, it's changing a little bit. Those GPS points are changing, and so I'm never going to get the same kind of content length. And so this is almost always going to fail, and that's why you see kind of that happening there. So I'm not really worried about these failed requests as long as it stays in this length bucket. But what I can see is requests per second, it's about 2.65. Now we weren't really exhausting. We just set this up. We just said do 1,000 requests. We didn't say do them concurrently or anything. I think it was just doing them one at a time. So it would do one, it would wait for that one to finish, and then it would do another, wait for that one to finish, and then do another. And you can see that the average kind of page load time is 50% of those pages were 371 milliseconds or less. 90% of the pages are under 400 milliseconds. And all of them, this is the longest request, 756 milliseconds. So let's change this just a little bit. The other thing that I can do here with Apache Benchmark is I can set another parameter called -c, and I can tell it how many concurrent requests I have. So, and as an example on this one, let's do 10 concurrent requests. So 10 requests at a time, and I'm going to do 1,000 requests total. So let's run this and just see what that does to our server. So it's already started. Go to glances. Now what I should see is you can see more of these PHP-FPMs, these being spawned up. And so we can see a bunch of demo ones. They're all in this R status. So that means that they're running, they're working. And my CPU usage, each one's about 10%. We're pegging 100% of our CPU. So we're maxed out a CPU on this. Memory, RAM, I'm okay. When I get to this point, I start to think, why did we spend so much time, calculating the amount of RAM and available RAM to figure out the total number of workers that I could have? And it feels like that's not even my constraint here. My constraint really is I'm CPU bound on this particular T2 micro. And that's okay, because in the next video, we're going to start to look at vertical scaling. And I want to modify my instance. So right now I'm using a T2 micro. What if I went to like a T2 2XL? So where I have like 8 cores and 32 gig of RAM. What happens then? I have to readjust my configuration settings, but then I should be able to run some performance testing, and I want to be able to kind of create a table and figure out what's the optimal instance and things like that. So that's what's coming up next, but I'm just kind of introducing the theoretical numbers. We put those in there, and then we introducing some tools here where we can do performance testing. So this particular benchmark, it's 400 in. I'm going to Control C to exit early. And what we can see now is of the 1,000, it completed 487. There's 482. They failed, all in the length category. I'm okay with that. Requests per second, I'm about 4.47 requests per second. And if you look down here at the page load time, half my pages are taking 2.2 seconds. So about 2.25 seconds, most of my pages, 90% of my pages are loaded. So in this video, we really kind of set the foundations for the next 2 videos that are coming up. This video, we talked about some of the fundamentals, like ensuring that we're deploying the latest versions, because those typically are fastest. Making sure that we have swap space available, and understanding caching and what that means at an application level. And then we talked about kind of the theoretical, the calculated numbers, the formulas for configurations for both FPM and NGINX. There's at least 2 more videos coming on scaling this web application. Next video, I want to look at some vertical scaling options. Right now, we're running this general purpose T2 instance here. And in fact, we're running this T2 micro. It has 1 virtual CPU and it has 1 kind of gigabyte of RAM. But you can see some of the other aspects of it. The T2 micro has network performance low to moderate. That probably has an impact on my web application. When I'm trying to transfer the page content or that payload from that server over to kind of the browser, the network, this network performance probably has an impact. What that impact is, we don't really know yet because we haven't done performance testing on these different instances. So the goal next time is I want to bounce between, I'm not going to hit all of them because there's a lot of instances here, especially if you start to go through, the compute, the memory, the accelerator. But if we just take a look at a few of these, like, compare T2 micro to T2 XL. What if I had 8 CPUs and 32 gig of RAM with a moderate network? What would that give me performance-wise? We're going to try to pull some numbers from the Apache Benchmark so we can have a consistent test. Given a server, I can set the optimal configuration, I can tweak some parameters, and then I can run a test, and then I can get some metrics out of that test, some numbers like requests per second, or transfer speed, or page load times, average page load time. My goal is to create kind of a spreadsheet of that data, and we'll make that data available to everybody, but that's going to be in the next instance. So I'm going to bounce between these T2 instances, but I'm going to bounce around between, we're at the T2 level. Maybe I'll look at M5s, see about M7 or MI. But then what about something that's memory optimized? What about something that's storage optimized? I mean, right now this PHP application, these are PHP, these are files on the disk. What if I get a storage optimized instance? Is that going to impact, how quickly I can read that PHP file from the disk, do kind of what PHP does in PHP-FPM, and then send the response out? I don't know, but we'll find out next time. So we're going to bounce around that next time. So this next video will be all on vertical scaling, and hopefully I'll just have some good data that we can just all share. The video after that, we'll talk about horizontal scaling. And I know Amazon has all this infrastructure available that we can just leverage. We can have application load balancer and this auto scaling groups and see if we can really kind of maximize that. But I think my first stab at this will be, what if this is all our own hardware? How would we load balance this if we didn't have this Amazon AWS infrastructure available to us? And we would probably use, for example, NGINX as a load balancer out front, have those TCP sockets going, and have multiple instances of the application behind that. So I'm trying to set something up in the first video where, this is something that maybe Amazon Oz, you don't have access to that. You're doing it on-prem. And then after that, we'll have another video on kind of diving into some of the Amazon AWS infrastructure and using that to horizontally scale your application. So anyways, that's some upcoming stuff. If you like this kind of content or you're excited to see those, go ahead and hit the like button, subscribe. If you have some specific suggestions you want to see, go ahead and add a comment below.